So hi, I'm Wenhao. I'm going to talk about modal effect types, which is joint work with my collaborators. Okay, I'll start with a recap of traditional effect types. So what are effects? There are many different descriptions, and my favorite one is that they are the way that programs interact with the environment. There are many examples like I/O concurrency, exceptions, and effect types statically track the use of effects in types. So let's see how traditional effect types work. Here is a very simple increment function that takes x and increments it by 1. And another simple higher order app function that takes the function f, takes parameter x, applies f to x. And if we apply app to inc to 42, we get 43, which is basic functional programming. The idea of traditional effect types is to annotate each function arrow with the effects that they use. So here we have these empty braces beside each function arrow, which mean empty effect, because these functions are pure. They are not doing any effectful computation. If we change the definition of inc to call an operation ask, which takes a unit, returns integer, intuitively it asks for an integer from the context. We need to track the usage of ask in types. So now it is a function from int to int, which performs ask. And in order to apply this higher order function app to inc, we also need to change the type of app to allow the argument to use the effect ask. And in general, in order to be able to apply app to any effectful function, we need to use an effect variable e to abstract over which effects can be performed. And since the argument f is also used in the definition of app, other arrows of app also have this effect variable e. Similarly, for inc, we also need to add an effect variable e in order to be able to use inc together with other effects. And here is a handler for ask, which takes a function argument and handles the ask operation of it by assuming the continuation r with 37. For the type of the argument, we have ask and e, which means this is the function that might perform ask. This ask operation is handled by the handler here, and it may also perform other effects e that is abstracted. So we can apply this handler to arbitrary effectful computation that may perform ask. So this is the basic idea of traditional effect types. As we can see, there are many effect variables like e almost appearing on every function arrow. This is especially painful if you want to add such a system to existing languages, because there are already many type signatures of higher order functions in the library code, and we need to change all of them to add these verbose effect variables. So the question is, can we get rid of these effect variables? And we proposed modal effect types to solve this problem. So let's take a closer look at the definition of app. It is a rather simple function, but has a very long type signature with these verbose effect variables e. And this is unfair, because app itself is an innocent, pure, higher order function, which does not perform any effects at all. Why do we need to add these effect variables to its type signature? Why don't we just track the fact that its definition does not mention any effects? But however, we can't do that, because in a traditional effect system, we have to annotate each function arrow with its effects consistently. So our idea is to decouple effects from function arrows. And the key concept for decoupling is ambient effect context, which is tracked by the typing judgment, which means the effects that are provided by the context. So here we have this app function, we have this @e, which is part of the typing judgment, which means that the context of this function provides effects e. And effect context propagates through the whole program. So for the argument function and the result function of app, their effect contexts are both e. In order to have some effect information in the type, we use modalities. The first one is the absolute modality, written as a square bracket with f, which means that for the program inside this modality, their effect context is f. So for app, since it is pure, we can use the empty square bracket to mean that we can use the empty square bracket, assuming the ambient effect context is e. This modality overrides e to empty. So we know that for this function inside, it is pure. Its effect context is empty. And we have a natural notion of sub-effecting, so that although f is a pure function, we can of course use it under any effect context e. Similarly, for ink, instead of having this quantifier of e and adding e to the function arrow, we can use an absolute modality to say that the definition of ink uses ask, and we do not care what other effects that might be used when we apply ink. By sub-effecting, we can still apply ink with other effects. We also have relative modality, which is in particular useful for handlers. So this is the handler for ask. It is a higher order function, as we have seen before. It takes the function, handles the ask operation of this function. With relative modality, we just need to specify which operation is handled by this handler. So assuming the ambient effect context is some effect is e, this modality adds the operation ask to the effect context e. So for the argument, its effect context is ask and e. This ask operation is introduced by this handler and is handled inside this function. So the outside context is still e. Yes. And of course, as itself is a pure function, it handles ask, but its definition does not use any actual effects. So we can also add this empty square bracket to keep the information that ans itself is pure. And by sub-effecting, we can apply ans to arbitrary effectful functions that might perform ask as well as some other effects. So this is the basic idea of modal effect types. Instead of having some quantifiers and effect variables, we use these succinct modalities to track effects. And we have the convention that global definitions implicitly have an empty square bracket because global definitions should be pure. So the types becomes more succinct. And we can, of course, compose them together. There's one example of applying app to ink and handles it by ans. And here is a more complicated example about cooperative concurrency. I'm not going into the details, but I'll just show the animation of the change over types. Yeah, and now I'll quickly introduce the first typing rule, which is modality introduction. to give you a flavor of how the system works. So we have this mode syntax, which introduces the modality for the result type and a knock to the context. And it overrides the ambient effect context E to ask. These knocks are used to control which variables can be used. So this is the usage of the variable. And we have these modality transformations to allow this variable f to be used after a knock. And in order to have such a variable binding like f annotated by some modality, we use modality elimination with the syntax net mode to eliminate. Here we eliminated the modality, the empty square bracket. Yeah, and there's more in the paper. We have a call calculators based on multimodal type theory inspired by Frank and effect. We also have masking. So our previous relative modality only adds effects to context, but we can also remove effects from the context. And standard meta theory, some extensions like standard polymorphism, algebraic data types, and a simple bidirectional typing, and some encodings. Yes, and we have an artifact, a prototype implementation. So there are also some ongoing work about a framework for encodings, and we are doing better type inference. I want to have a formal comparison with some with capture tracking, and also like distributional semantics and higher order effects. So I think my takeaway is do not track effects of function arrow. Instead, track them when needed and track them with modalities. Thank you.
We have time for some questions.
This looks really cool. I was just wondering how things behave then when you're doing sort of lambda abstraction. Mm-hmm. Am I right in thinking that essentially the modal context of the body is just the same as the modal context of, yeah?
Exactly.
Okay,
yes.
So it's a sort of contextual style effect.
Yes.
Yeah, okay, yes. Yeah, that makes sense. So it's not like captured inside.
Yes.
Yeah.
Yes, so function by default do not do anything to the effect context. And the effect context is only changed when we introduce modalities.
Right, great. Okay, thanks.
Thank you.
Hey, so Scala 3 does something similar with capabilities. Mm-hmm. Can you compare it a little bit with that?
This is one of the first work that I'm listing here. And we have compared between effect, which is a research language with capabilities, and our work, but we haven't do the comparison with Scala, and I want to do that. Okay.
It seemed like you added the mod expression constructor. Could you go into that a little bit more?
Sorry, could you say again?
You had also a new expression term, which was this mod thing, I think it was called.
Yes.
Could you go into that a bit more about what that means? Besides the effect on the types, like how is it, does it have an operational effect or is it just a type effect?
Oh, well, it is just an explicit syntax for introducing modality. It is very similar, like if you think of system F, it also has this big lambda alpha, which is an explicit syntax to introduce a type variable. And here, what's happening is very similar.
So it's sort of like a mini type annotation in a sense.
Yes,
okay.
You can understand it.
Okay, let's thank Wenhao again.